Dear students, I would like to welcome you to our second exercise of the lecture Integrity of Materials and Structures, and the topic, the theme is today axle in the bearing of the returning sheave of a chairlift. And this axle was fractured, and of course it's a very dangerous accident which may happen here. So we first have a look at the design. It's not really from that case, but it is similar to that. We see here the axle, and first the history of the axle was about 1,700 hours of service, and that correlates to about 1 year of serving time. And we were told by the client, by the manufacturer of this kind of machine, that about 100 axles were running without any problems for many years. Now when we look at this design, we see here now this axle where we are talking about, and the axle makes, of course, transfers the energy, the power from the machine to this wheel, and on this wheel you see here the ropes, and there is attached the chairs, and this axle is continuously running, and what we already know, there is of course a changing load. Sometimes there is more people, sometimes there is less people, and then also when this chair is passing here, so we do have doing continuously rotating a changing load. And what I also have to tell you, in the morning when the man who was responsible for that machine, he started the machine, and he heard a sort of a scratching here, and a loud noise, and for that reason he said, oh, there is something wrong, I have to find out what's going on, and he switched off the machine. And then finally, with another technician, they investigated in that area, and they saw that there was something loosened. So they acted really quite responsible, because if you can imagine, when this part here breaks, then the whole components come down, the rope will crash, and also of course all the seats of the chairlift will crash down, and maybe people can be very much injured. Now, as all the time the same, we have to ask ourselves, what kind of mechanical loading is on this kind of design, on this component? First, what we think of is clear, that this wheel here has a certain weight. So there is a weight, a stress just here going down. However, that's not the main load. You may think very carefully what other load is coming on. And then you think about that there is here, this like the axle, and then we have here the rope. And what does the rope make with this kind of wheel and the stress on the axle? It wants to bend it in this direction, wants to bend it in this direction. So what we also now already know, that this during service is rotating, there is a change in load, and there is a bending moment on this axle. So how do we call this? It's called rotating bending fatigue. Fatigue due to the fact that there is a change in load, and again bending of the axle. It's very important. For those who are really experts in mechanics, I have to tell you, when the machine starts, there is in the first second, until it's really running continuously, in the first seconds there is a torsional moment on that, but this stabilizes after a while when we have continuous movement. So this is now, it's very important all the time that we think about the mechanical loading of this component. Now the next slide shows us the technical drawing, the design and the material. What we see first here, this is our axle, and this is our returning sheave, this wheel here around, only a part of it. And this axle, here you see it's a low alloyed steel made from 34 chromium nickel molybdenum 6. This is a German designation. It tells us it's 0.34 carbon inside. Chromium, it's not 6, it's divided by 4, so it's 1.5% chromium, and nickel and molybdenum is less than 1%. And you know, of course, the purpose of these elements is just to increase the strength of this steel. But it's a very normal steel, this low alloyed steel, it's not very complicated. And now the design, this return sheave here, what we see here, this big wheel, how is it manufactured? It's applied on this axle by putting it before in a big furnace, heat it up, and then you put this wheel on the axle and let it cool down. So it's shrinked on that axle. Now, for locking this, you see here so-called keyway, that's for locking the return sheave. And additionally, of course it's now very important for us, I tell you, the fracture surface, it was totally fractured. This axle is in this plane here. And it's about 30 millimeters from here to that place. I have to tell you, it's also very important to keep in mind that the main stress on this component is in this corner. So the fracture occurred not in the main stress area, it occurred here. Keep in mind that. Okay, now it's clear we have to investigate this, and this part here, which we see here, which is fractured, was carefully removed and brought to our laboratory. Of course, it was then just cut here, and then this part we will investigate very carefully. And this part was still stuck. So again, this for investigation. And this, in the next slide, we have a look at it. Looks like that. You see here our fracture surface. You see here that part until here was stuck inside, was shrinked, where the wheel was shrinked on it. And here you see this bundle for the securing ring. I would say in the next slide you see it much better, because we have to ask ourselves now what kind of fracture we do have here. And we have to investigate and find it out. And you may think very carefully first when you watch at this fracture surface what kind of fracture we do have here. When I think of the students from the recent years, there were all the time different possibilities discussed, and also somebody said, for instance, yes, maybe the fracture started here. Or somebody said, oh, maybe the fracture started here, or here, or here. Now you think very carefully. Normally, I think we can exclude that a fracture starts here from inside. Why? Because there is a very, very low stress originally on the component. We know already the high stresses are all the time outside, on the surface of the component. And now something else is coming up. We remember the loading of this component, and the loading was rotating, bending, fatigue. So there is again fatigue coming up. And what do we know from our first lecture? When we are watching for signs of fatigue, there is one really important feature. How is it called? It's called our beach marks. Of course, this is now again reality, and it's not so easy to find out here any beach marks. And I do have really even, it's quite heavy, this original part here. And if I would show this you around, then you can, under a certain angle, recognize some lines. And these lines I see, for instance, here, that, or in that direction, or here. It's difficult to see, but maybe also on the slide you may recognize there is here, for instance, you can see this here, or here, parallel lines. When you follow them, they show us here in the middle of that half elliptical lines of these zones that there is most probably in this area the crack initiation site. And this holds also for here and here. So what we can at this moment already keep in mind, that we do have here 3 fatigue cracks going slowly together during service, during this about 1 year. And what we do see here, this is our final fracture. Now this is very crazy, huh? When we think about that this very big component has only this very, very small final fracture. That means that during running, maybe a few days before, it was still running and only the stress was taken over by this very, very small part. So that means the original nominal stress on this component was relatively low, very low. So the dimension in principle of this axle is totally right, it's fine from the pure mechanical point of view. So this makes it even more mysterious that this very big component had these 3 cracks and starting to grow here inside. So we have to investigate this very carefully to find out what happened here. And I can tell you, we did a lot of investigations, and for a long time we really were not sure what's going on. Now, that shows us at the edge of this fracture surface, there is a surface of the axle, there is a dark corrosion layer, we keep in mind. Or here, that is again our axle surface, this is a bundle, and what do we see here? Of course, this is coming, this massive fretting due to removal of the axle. You have to imagine this axle was, over this axle was stuck the wheel, and it was still shrinked even after the fracture, and it has to be removed. So this is just secondary, we keep in mind. Okay, now the investigation starts, of course, after first visual inspection, as I told you, on this axle fracture surface. You easily can, not easily, but you could see these beach marks just by visual inspection. But at higher magnification, we have now investigations here at the edge, at the start of the cracks. Because again, due to these half elliptical zones, we assume that here the crack started. And now something very interesting is coming up. We have a look here in this area by scanning electron microscope, and this shows us the magnification. Now, what kind of fracture surface do we see here? I think it's quite easy to recognize when we watch at this here. What's that? What's that? What's that? This is all grains. The surface of grains. It's a grain surface, so it's an intergranular fracture. But what we already know from fatigue cracking, even also, especially at the start, at the initiation, the crack is not at all intergranular. It's a transgranular feather-like structure. However, I can tell you this kind of feature, this intergranular structure, was only until a depth of about 2 millimeters here inside at all of the three fatigue cracks, fatigue surfaces. Then the crack transferred to transgranular growing. So we keep in mind there is something very special going on at the outside, at the start of that crack, and it's an intergranular fracture. Now it's very important to have a look at the adjacent crack initiation site on the surface of that axle. And we see here again at higher magnification in the scanning electron microscope the surface here just nearby of the crack initiation. So what do we see there? There is mainly two features. One feature, these parallel lines. What's that? That's no problem. This is at higher magnification. You have to imagine this is from the production of that component, which is merely done by turning with a tool, and this is just the turning lines from the machining of this component. So this is no problem. So the roughness is relatively low, but we see something else. What is this here? What's that? There's different possibilities. There's also a possibility, which was argued, that there is something stuck, another material here on the surface. How can we investigate this? Very easily. We can make here, when we are anyway in the scanning electron microscope, we can make X-ray analysis in the microscope, and I can tell you, we only could find the elements of the steel, nothing else. So there's another possibility, and of course, when we know a little bit from literature what may go on, this is all very small holes, and it's a combination also. These holes are coming from a small corrosion attack, and they have the name corrosion pits. So here are corrosion pits. The question is why they are coming from and what is their influence. This, you imagine this scale here, they are very, very small, and finally we have here this component, this axle with such a big diameter. How can they influence that there really starts a crack and growing here inside? It's unbelievable. It's really unbelievable. But for this, to get more idea what's going on about this mystery, it's a real mystery, the next step is to cut here inside, because when we cut here inside, then we can take out material, and we even can watch perpendicular to this area here inside in the material, and we can see what's going on underneath of these corrosion pits. And this is shown in the next image. It's an optical microscope image. This is now the surface which correlates to here, the surface of our axle. This is a steel here, and this is an embedding material. And that's a scale. So what do we recognize here? Now exactly, when we go back to this, that's a corrosion pit. And again here, that's a corrosion pit. Now we cut through. And more important, at the ground of this corrosion pit started cracks growing inside in the material. So that's the initial state. Of course, these cracks here underneath here by the time lose the power to grow, because the main stress and the main crack was going here and then they stopped. But obviously that is very clear, this kind of mechanism was the main point starting for that crack here. What we know a little bit about corrosion and pitting corrosion is by the time here in this pit, the environment will change by the time. There is more aggressive inside in this pit, and it's just formed by humidity. You only need water, nothing else. And secondly, it's a small effect, but it's an increasing effect already at the bottom of that pit. We have also already a little bit a higher mechanical stress. So the mechanical stress here inside is higher compared to here. And of course, when then a crack is growing here inside, slightly the mechanical stress increases here at the crack tip. This is also this is pure mechanical engineering. There is an increase of the stress at the crack tip. So there is, at the very beginning, the influence of corrosion is very high, but by the time when the crack is growing and first pushed inside by corrosion, but by the time when the crack is growing and growing, the amount of the mechanical stress, the mechanical part, increases. And obviously, we remember that story before, at a depth of 2 millimeters, so this is an intergranular fracture due to corrosion, and at a depth of 2 millimeters, then the mechanical part will be higher, and the crack growth will be dominated by mechanical stress. But this is very much deeper, so that's the initial start. Okay, at this point, there is also another example how the corrosion really acts very crazy. We have here the fracture surface itself somewhere inside, and there is even perpendicular to the stress level also cracks, only dominated by corrosion. This is another example. Okay, now I can tell you we performed so many tests. We tested the material was fine, the mechanical properties were met, and the microstructure was fine, chemical analysis was okay, and we were thinking what's going on, and it was really still a mystery. However, and I can tell you, I traced back our investigation, and I can tell you we made a very, very big mistake, and this mistake will come up and we talk about. The one point first I have to point out to tell you, when we have a look in the literature for fatigue and for rotating fatigue, there is never any example why the cracks start just at 3 points. Because in principle you can imagine when this axle here rotates, all the spots at the surface have more or less the same stress. So in that cases we do have a lot of crack initiation sites, maybe 50, 60, 70 or so on, all around the surface, but not 3. And then we come back to that where we're thinking very carefully, and besides here we see again our technical drawing of the design. And when we watch very carefully, again, this is now our axle again, there is a fracture surface, this is now in this area the wheel, the returning sheath, shrinked on it, and we recognize something. There is a screw, but only on one side is a screw. And now, sorry, I do not have this available anymore. I can tell you, when you have a look from the top view of the drawing of this design, then we see there not only one, or here screw, we see 3 screws in a distance of 120 degrees. And this correlates very nice with this, what we can see here. And at this moment, when there was a next meeting with our client, with the owner of the factory, who was all the time very crazy about us, that we didn't find out what's happening. And then I asked him, can you please tell me what's going on with these screws? Oh, then he told me, oh, sorry, I forgot you to tell. This minor change we put here inside. Additionally, 3 screws. All the other designs, the 100 axles before, they didn't have these 3 screws and this bundle and this securing. So that was in this special design new. So in that moment, for us it was clear that there is a correlation between these screws, 3 screws and 3 fracture surfaces on this failure. Now the question is coming up, and this we could also trace back, that the screw, is it now located here or is it here? Think carefully about this. I can tell you, we could trace back that the screws were all located here, here and here, and not here. And we will have also later on an explanation for that. Okay, so we already start the first result. As I already told you, we made a lot of investigations. The microstructure of the steel was okay. The chemical analysis was okay. Mechanical strengths, tensile properties, everything fine. And we measured even the residual stresses on the surface of the axle, and they were compressive, even beneficial. Now, what is the real mechanism? As we have already seen from our findings, again here the surface with the corrosion pits, then here the image, the metallographic specimen with the corrosion pit and the cracks, and here the scanning electron microscope. At the very beginning we do have pitting corrosion and the intergranular fracture until a depth of 2 mm. That means corrosion dominates in the initial state of the fracture. As again I told you, a minor change of the construction, secure ring fixed by 3 screws. And now it's coming up. When we have a look then at the design again, I already tell you, this does not allow any drying of the moisture. We all the time have moisture around, the metal is cold, the air is wet, and then it can, the humidity especially transferred to this metal part. And I have to tell you, this is corrosion, no specific corrosive element is needed. We are here high up in the mountain, there is no chlorine around, no sulfur, so it's very, very clear. It's not necessary. And we also keep in mind, again, this mystery that there was a very, very small overload fracture. However, obviously, due to the mechanism, first slowly corrosion, cracks start to go inside, propagate inside more and more. Then on the crack tip, the stress increases, and additionally we have here a different chemical environment by the time, and this pushes the crack forward. Now back to this design, which was changed. We see here, that was here the area of the fracture, and here we investigated and found all these features of corrosion pitting. Now, what's happening? During service, that's important, when the machine is running, and this is a reason why the crack started not here, because here it's tight where there is the screws. The cracks started here between, because you can imagine when the machine is running and here it's fixed and here it is a sort of a breathing. There is a little bit opening of that gap. A few micrometers is enough, and these micrometers suck inside the humid air, and the humidity, the moisture, stays here inside. When the machine is switched off, it cannot dry. And the original design, where there was no bundle and no screws, then obviously it could also breathe a little bit of gap, humidity, but it was not trapped. Not trapped. Look here, this is trapped by this design. So the moisture, the humidity is trapped here, and this makes here this corrosion pits, the start of it. So again, that was the explanation that 100 axles were running very well, and then we just told the client, the manufacturer, just remove this here. It was a good idea to make it better, but they didn't make it better. From the mechanical point of view, they made it better, but from the corrosion point of view, they made it extremely worse that this fracture occurred. So make it better, remove all this again. It's safe just with the shrinking, and they made it also with the future axles, with the future chairlifts, and nothing else happened anymore. So that was an extremely lesson for us and also for the manufacturer, that this may happen, because again this component has a very, very low nominal stress. However, due to this mechanism, crevice and pitting corrosion, this could happen here. Okay, so again, so we are here at the end of this kind of lecture, and if you have any contacts, please write an email to me, or you even may have a telephone call. And at the end, I wish you really in these difficult times good health, and I hope to see you again next week. Thank you very much.